Assalamualaikum and salam sejahtera. Doing chapter summary for chapter 5, Electromagnetic Induction. So for this chapter, we have 5 subtopics. We start with magnetic flux, induced EMF, self-inductance, mutual inductance, and last one is the energy stored in an inductor. For the first subtopic is magnetic flux. The question is, so this is a symbol for magnetic flux, BA cos theta. B is the magnetic field strength, A is the area, and angle theta here is the angle between the normal area. So this is the plane of certain area. So the normal area is perpendicularly to the plane of that area. And it must be the angle between, the theta here is the angle between normal area and the magnetic field. And the unit for magnetic flux is Weber, the specific unit. You can also find the magnetic flux linkage. This is also known as the total magnetic flux. For this quantity, it is equal to the number of turns multiplied with the magnetic flux, or if you expand the equation, magnetic flux is equal to BA cos theta. Then you'll have NBA cos theta. So the next subtopic is the induced EMF. This induced EMF is basically produced or proven by the Faraday's law experiment. So we have a relationship between the change in magnetic flux with respect to certain time, or the rate of change of magnetic flux. When we have the rate of change of magnetic flux, or the EMF will be induced. So it is directly proportional. And from the value of induced EMF, we can have the current induced. As we know, E equal to IR. Expanding this basic equation, you'll get formula for the EMF, or for a more general equation for the induced EMF is E equal to negative N d phi over dt or negative N dBA over dt. And for 5.2, we also have Lenz law that is related to the direction, okay, that is opposing the changes of the magnetic flux in the original circuit. For the induced EMF, okay, we have 3 specific cases. The first one is the induced EMF for straight conductor, and then we have the induced EMF in coil, and last one is the induced EMF in rotating coil. So you have 3 cases. Case number 1, case number 2, case number 3. So for all these 3 cases, we are actually deriving the equation from this basic equation. From the derivation, we have, for straight conductor, you have EMF equal to BLV sin theta. And to determine the direction of current or velocity, okay, or the magnetic field, we are applying the right hand rule. So we have V terms representing V, B, and I. Okay, so this is the rule that you are going to use to determine the direction of either V or B or current. Okay, so V here is the velocity, B is the magnetic field strength, and L is of the straight conductor or rod. So for this case, your straight conductor is in the region of magnetic field, and it must be moving with the velocity V. We can always relate our EMF with the basic equation E equal to IR. Okay, so you can also find induced current from this equation. And for the second case, you have the induced EMF in coil. That is, the first equation is if the area changing, so negative N dB dA over dt. And the second possible equation for the case of coil is the magnetic field changing. So A is constant, so it's going to be negative NA dB over dt. And last one is you have the rotating coil. So when the coil is rotating, it must have omega, that is angular velocity. So your equation must consist of NBA omega sine omega t. So basically omega t here is equal to theta. It is coming from the equation angular velocity is equal to angular displacement over time. So overall, for all 3 cases, you have 4 equations. First one, second, third, and fourth equation. and it is all coming from this basic equation of Faraday's law and Lenz law. But for the third subtopic is about self-inductance. So self-inductance is basically the induced EMF or the induced current is coming from the same circuit. Okay, so that's why we call it as self-inductance. Originally is from a circuit, and the induced EMF is from the same circuit. And we also have mutual inductance. Okay, so for mutual inductance, when we mention mutual, means we have to have more than one coil or a solenoid. So it's either the coil is placed next to each other, so this coil is sharing the same flux, so that's why we call it as mutual inductance. Or it can be coaxial. It means that coil number 1 is inside coil number 2. So we have two possible position of coil 1 and coil 2 for mutual inductance. So in terms of equation, this is the equation for self-inductance. The basic equation, EMF over di per dt. Negative is because of the Lenz law, and phi over I. If you are calculating the self-inductance for the coil, it's mu naught n squared A over 2R. And if it is for the solenoid, it's mu naught n squared A over L. For equation number 3 and equation number 4, it is actually derived from the equation L equal to n phi over I. We expand the magnetic flux B A cos theta. So B here is referring to the B of the coil, okay, or B of the solenoid. Okay, you can refer the equation from chapter 4. Then that's how you get these two equations. For the mutual inductance, the pattern of the equation is just about the same with the self-inductance. Okay, if you could see from the screen here, the pattern are just about the same. So this is for the basic equation. We have EMF, we have di per dt, and we have n phi over I or n2 phi 2 over I1. But for the mutual inductance, we only have one derived equation. It's mu naught n1 and 2a over L. And the unit for both inductance, self and mutual inductance, is Henry. Okay, and last one is we have the energy stored in inductor. So this is the only equation, is half Li squared, and of course the unit is joule. We have a case in determining the equation of the determining the direction of the induced EMF. So for this case, induced EMF or induced current, we have to look at the case. Is either if your case is having magnetic field increase, especially for this case, because we have changing magnetic field. So if the B is increasing, B original increasing, your B induced or the induced magnetic field for this case will be having the opposite direction. So for example, the original magnetic field is into the page. The induced magnetic field will be out of the page because it is opposite. It is out of the page. So this is the direction of B induced. So for example, this is the case of a coil. So if the magnetic field is out of the page, let's say this is your coil, so then you'll apply your right hand grip rule. For this case, your thumb is pointing out to your face because it is out of the page. Then you'll have your direction of current is anti-clockwise, okay, from the right hand grip rule. Okay, using your right hand, and then you grip your right hand, then you have your current is anti-clockwise because your magnetic field is out of the page. On the other hand, if you have the case that is your B original is decreasing, so your B induced will be same direction, in the similar direction. So if B original is into the page, so your B induced is also into the page. Then your direction of current using your using your right hand grip rule, then your direction of current will be clockwise. So this is current induced. Okay, induced current. So question normally asks us to determine the direction of induced current. So we use this method. So how can we get this condition? Okay, condition number 1 and condition number 2 is from the Lenz law that we have learned. Okay, induced EMF. So that's all for chapter 5. Thank you very much.